Okay, so hello there. In this video, we will try to answer this question provided here. Consider the polar curve r equals 2 cosine theta. What is the area enclosed by one loop of this curve? So in order for us to answer this, we need to first determine the formula that we need for this question. So surely we're gonna need a bit of integral calculus to answer this. So remember that the area enclosed by a polar curve, say r, which is equal to a function of theta, that is from theta to theta. Let's just denote it as the lower limit theta is alpha, and up until 2, the second theta, which is your beta, is given by this formula. So we have the area is equal to 1/2 the integral from alpha to beta r squared d theta. So that's our formula right there. So from this, we need to then be able to determine what are the limits of our integration. So since we know that our curve is, since our curve is r equals 2 cosine theta, the curve starts at, just some characterization. So it starts at theta equals 0, and it should return to the origin. Okay, this returns to the origin when r equals 0. So let's fit that. Which actually this happens this is at theta at pi over 2. But however, we will not be only until pi over 2. We need to consider from 0 to pi, because we want a full loop here. So we want to have to consider 0 to pi. So if that's the case, we should be therefore considering one loop. Hence, our lower limit alpha will be going to 0, and our upper limit beta will be up until pi. So that's the limits of our integration or integrals. So after that, we need to set up the integral given this information right here. So that will be step number 3. So we need to move a bit. Okay. So for the third step, we need to substitute. What we will be doing is we substitute our r equals 2 cosine theta into the area formula, which is given here above, this one here. So we want to substitute it here, okay, into star. I'll just call that asterisk. I'm just gonna denote that some asterisk here. So what we have is, therefore, let me move. Okay, a is equal to 1/2 integral from 0 to pi. That is, since our r, remember it's r squared, so our r is 2 cosine theta. So that becomes, all right, let me start with r squared d theta. That will become eventually 1/2 0 to pi 2 cosine theta d theta. Okay, I hope that makes it clear. So we want to substitute that, of course. Oh, I forgot. There should be a square there. We need to finalize that, and we want to make it. Put a square or redistribute it. Just the normal PEMDAS, the e part. So 2 squared is 4, and cosine theta squared is cosine squared theta d theta. So that's a picture of it. That's the next step would be, we can actually, there's a property in integrals where we can move this this number here inside the integral sign. It's a constant. We can transfer it outside. So that's what we're gonna do. So what we have is, 1/2 times 4 from 0 to theta cosine squared theta d theta. So we know 1/2 times 4 is going to give us 2. So therefore, 2, the integral from 0, that runs from 0 to pi cosine theta, cosine squared theta d theta. All right, so in this part, we can actually, we're done setting up the integral. That will be the last part here. So eventually this becomes that our area is equal to this one. So we can actually then evaluate the integral. We will use the identity for cosine squared. So remember, identity for cosine squared theta is given by cosine squared theta is equal to 1 plus cosine 2 theta over 2. So I'm gonna call that star here. We're gonna use that later on in our here. Okay, so since we have cosine squared here, so we're gonna distribute that, or we're going to substitute that. So using this, so using star, we have our area A is equal to 2, 0 up until pi cosine squared theta d theta. So we're going to use this star identity here. So this becomes equal to 2, 0 to pi. Okay, this becomes 1 plus cosine 2 theta over 2 d theta, of course. So with this, we can actually perform the same thing that we did this portion from this portion, which we let out the 4 here. So what we're going to do is we're going to let out the 2. Well, not really the 2, the 1/2. So we can factor out 1/2 in this term, and this becomes, let me move a little. This becomes 2 times 1/2 integral 0 to pi. This time it's not cosine squared, it's 1 plus cosine squared. So I'm going to call that 1 plus cosine, not squared, cosine 2 theta d theta. And to erase the ambiguity, I'm just going to put a parenthesis here so that we won't get lost. Okay, so clearly this will become 1. We can clearly have 0 to theta, 1 plus cosine 2 theta d theta. Okay. All right. So from here, we can actually use a property of integrals where we can split this two. Move a bit. How do we split this? We can imagine that, a moment. There's a plus sign here, so we can split this. We can put an integral sign in the 1, integral sign in the cosine 2 theta. So we can do that. What we have is this becomes, for the first integral and the second integral as well, we have, I'm just going to move it here, 0 to pi 1 d theta. That's the first step. And then this becomes plus integral 0 to pi cosine 2 theta d theta. And then we're going to evaluate them one by one here. So I think it's better if we're going to put a big bracket in both of them so that we can evaluate them separately. So what we have is, for this one, so we want to make it, well, this becomes a theta. So it becomes 0 to theta, right? So if you have a constant, you just need to change it into that number. So if you want it to be step by step, we have theta from 0 to theta right there. And we're gonna leave that for now. Here, we want to integrate cosine 2 theta. And if you're gonna look at your the books, this becomes pretty much sine 2 theta over 2, 0 to pi. Okay, so it's pretty clear now, since we are in with respect to d theta, this theta here will clearly become simply pi, okay, and plus this becomes here. So if you want it to be step by step, so what we have is, I'm just gonna still put that in a big bracket, sine 2 theta over 2 minus sine 0, that's 0 because that's our lower limit. Let me put that in a parentheses, over 2. And we can actually simplify this, and eventually we'll see that this becomes, this whole part here will become 0. So what we have is, this is going to be equal to pi plus 0, and that's your area under the given one loop. So pi plus 0 is clearly pi, so therefore your area is equal to pi. And that is our final answer. So therefore, to find the answer, or to state it properly, the area enclosed by one loop by the polar curve, what's the name of the polar curve there? The polar curve r equals 2 cosine theta, and which is enclosed after one loop, the answer is equal to pi. Okay, I hope that answered the question, and thank you very much for listening. I hope you learned something from here, and thank you very much. I'm going to see you in the next video. Bye.